everyone to my presentation of this work. The topic is the study of a very particular type of contractions that are studied in the framework of the MMP under a numerical length condition. Right. So, as I said, the general framework is that of the minimal model program. I don't know if everyone is familiar with that. Probably not. But basically, the idea is if I start from a smooth variety, so algebraic variety, complex, everything is over the field of complex numbers. And this variety, which I can assume to be projective, then the question is, which is still an open question, the answer in general is not known, does there exist a birational representative x prime of x with nef canonically nef canonical bundle? So, okay, birational representative means a variety x prime which is isomorphic to x on a dense open subset, but not necessarily everywhere, right? And the canonical bundle, which I denote as kx prime, that's the canonical bundle of x prime. For x, it would be kx, of course. The canonical bundle is, well, that's a line bundle on x prime, which is expressed as the determinant of the cotangent bundle, right? So ideally, this would be the situation that we want to have in the MMP. Sometimes it's not possible, and we can expect to have the opposite situation, which is that x prime has the structure of a fibration of something else, of lower dimension, of course, and the general fiber is Fano, so meaning that on the general fiber, the anti-canonical is ample. Okay, so these are the two opposite ending situations that we want to have in the MMP, and we call these final objects. And the theory developed by some Japanese guy, Mori, in the 60s and in the 80s mostly, and the 70s, follows from the following idea. If my variety x contains a negative curve, so negative curve means a curve containing x on which the canonical has a negative degree, so that's this curve is a witness of the fact that kx is not nef. I want to contract this curve, and I want to forget it so that I get closer and closer to a representative of x with nef canonical, right? And well, to study these negative curves in x, Mori constructed a cone, a geometric object. This cone, which we usually call the Mori cone of x, is, it's contained in a vector space over R. So this vector space N1x of R is this vector space generated by the curves in x. So just formal linear combinations with R coefficients of curves in x, but I quotient out by the numerical equivalence, meaning, well, two curves are numerical equivalent if any line bundle has the same degree on both of them, right? And this cone in this vector space is that cone generated by, curves in x with only positive coefficients. Right, so we call this the Mori cone, or the closed cone of effective one cycles. Right. And in this cone, which is generated by the actual curves in x, I want to identify the part on which kx has negative degree. That's what this very famous and large theorem by Mori studies. So I know, thanks to this theorem, that I only need to identify a countable family of rational curves in x, which are all like this. So they are all kx negative, right? Such that the kx negative part of the Mori cone, meaning the part which consists of those one cycles on which kx has negative degree, is generated by this countable sum of numerical equivalence classes of rational curves, right? And moreover, I know that this we usually say that this countable family of extremal rays is locally polyhedral. More precisely, what I mean is that an accumulation of such rays, so an accumulation as in having a limit, right? An accumulation of such rays can only happen towards the hyperplane on which kx has 0 degree, right? So if I move a little bit away from the vanishing hyperplane of kx, then the negative part becomes well, just polyhedral in the usual sense. Okay, so far so good. Of course, if anyone has any question about any notion, don't hesitate to interrupt me, right? Okay. So yes, so in that sense, these negative rays are the extremal. These are the rays generated by the extremal negative curves, right? If I want to contract negative curves inside X, so Kx negative curves, the best approach would be to contract curves which are in the negative extremal rays, right? So these gamma I want to contract. And well, the second part of this large theorem by Mori, often called contraction theorem also, says that if I have an extremal ray, so generated by this numerical equivalence class of a rational curve in X, if I have this extremal ray, which is Kx negative in the Mori cone of X, then there exists a morphism from X to a normal variety, which satisfies all these properties. So the fibers are connected, and the anti-canonical is relatively ample. And it is elementary in the sense that all the curves contracted by F are numerically proportional. So all the curves contracted by F all have their numerical equivalence class in the same extremal ray. Right, and this is also translated by the fact that the relative Picard number is equal to 1. It also means that I cannot factorize F through another contraction of this type, right? And this correspondence is 1-to-1. So we have a bijection between the set of Kx negative extremal rays and the set of such morphisms. And such morphisms we call elementary Mori contractions from X. Right, which can be either of two type. It can be either birational, that's the case where the dimension of X and the dimension of the arriving variety is the same. So on an open subset, F is an isomorphism, right? Or it can be a fibration, so we say a fiber type, which is the case where the starting dimension is higher than the ending dimension, and the locus covered by the contracted curves is total in X, right? And in a sense, this situation, so the second situation where F is birational is more, let's say it's more frequent in the Mori program. And the first situation, the situation where the dimension of X is larger than the dimension of Y, is that of a Fano-fiber space. So that's the same definition. That's the definition of that kind of object where I have a fibration over something normal with general fiber Fano, right? This situation is the situation of Fano-fiber space. So it is a final object of the Mori program, and that's an object where I cannot apply more transformations to hope obtaining something with Neff canonical bundle. Right? So these are two opposite situations. Okay, so for such a contraction F.
Sorry, Bruno, I have a question. What do you mean by Kx is relatively ample?
So
In the birational case, for instance,
Yes. Well, Kx and minus Kx, they are line bundles, right? So When I denote by minus, I mean the dual of the associated line bundle. So Kx is, in a way, the line bundle, which is the determinant of the cotangent, and minus Kx is the dual of this line bundle, and relatively ample means that it is ample on any fiber. So if I take this line bundle and I restrict it to any fiber, it's ample. Are you okay with that? Do you?
Okay,
Do I need to explain what ample means?
No, okay.
Okay.
And so in the birational case, the
Yeah.
condition is empty, yeah? Because the fibers are points, yeah.
Most fibers are points, but I can have a locus which is contracted with fibers of positive dimension. I can imagine like a situation where X, like on a dense open subset, it doesn't move, but there is like a contracted divisor, for instance.
Okay.
Yeah, the topic is just I identify a curve which is negative in X and I contract it, and I contract all the curves which are in the same family. And I obtain something else, but the dimension sometimes doesn't move, right? Okay. So for such a contraction, I define the locus of F as, well, that's the locus which is contracted by F. So this is the locus covered in X by curves which are contracted. Okay, so if the associated extremal ray is R, then this is exactly that, right? And well, when F is birational, this locus in X has positive codimension, and outside of it, F is an isomorphism. Okay. So now the numerical invariant that I need, the length. And this use of the word length is, well, you will see it. It has a geometric meaning. Well, the length of F is defined as the minimum that the anti-canonical of X minus Kx can have on the contracted rational curves. So that's a positive natural number, right? Since minus Kx is relatively ample, this can only be non-negative, like positive integer. Okay, and well, this this numerical value in a way tells us how far the contracted ray is from being positive. So I can consider this extremal ray in the negative part of the Mori cone, and I consider the generating rational curve inside it, and in a way, not to be very accurate, but in a way, this tells us how far this generating rational curve is from being in the kx, vanishing kx part of the cone, right? It's not like really a distance, but it tells us about how far this ray is from being positive. Okay, and well, this invariant is also very useful thanks to, well, first we know that it appears in this inequality, which holds thanks to a result by Ionescu and Wisniewsi. So we have this inequality where E is defined to be any irreducible component of the locus of F, and I take big F to be any fiber inside E, right? Of course, so the case of fiber type, where the dimension of X is larger than the dimension of the ending variety, is the case where E is equal to X. So dimension of X and dimension of E cancel each other on both ends of the inequality. But there are cases where E has positive codimension in X. Okay, and this inequality gives rise to the notion of contraction of maximal length. That's the case where the length, well, the inequality is met, right? And also, well, the notion of contraction of submaximal length. That's not the case where the length of F is maximal, but the case where the length of F is equal to its upper bound minus 1. Okay, as I precise here. So if there exists E and F such that the equality is met, then I said that the length is maximal, and I said that it is submaximal if it's equal to its upper bound minus 1. All right. Well, I can consider also the case where the length is submaximal, for instance, and so on. But these cases are very interesting, and because they give us a lot of tools. For instance, this case is one where we identified rather quick. I mean, not we, but mathematicians identified rather quick that the general fiber of F in that case is isomorphic to a projective space. And in this case, it was identified rather quick too that the general fiber of F, I mean that of positive dimension, of course, is isomorphic either to a quadric or to a projective space. Right. So, well, in that situation, my focus is the study of the structure of F. So F is considered to be any elementary Mori contraction under this numerical condition or this numerical condition. I want to study the structure of F. And, well, in other words, I want to find the birational representative of F, which has a nice structure, right? Okay, so what happens when the length is maximal? This is a work which was undertaken by my PhD advisor, and it was also based on a work by Cho, Miyako, and Shepard-Brown from 2002. As I said, if the length is maximal, then, well, let's say that it is a fiber type, but it's also true if F is assumed to be birational and the general positive dimensional fiber is assumed to be smooth, right? But, well, if F is a fiber type and the length is maximal, then the general fiber is isomorphic to a projective space. And this is true, as I said, thanks to a result by Cho, Miyako, and Shepard-Brown, which says that on the general fiber F, since the degree of the anticanonical of F on any rational curve inside F is more than is at least equal to the dimension of F plus 1, then we know that F is equal to Pn. And this theorem by Andreas Höring and Carla Novelli from 2013 tells us that well, since I know that as I know that the general fiber is isomorphic to a projective space, then I can try to degenerate this projective space and obtain something which resembles the projective space. And well, the result they came up with is the following: if I have an elementary Mori contraction of maximal length and fiber type, which is equidimensional, then it is a projective bundle, meaning that all fibers are projective spaces of the same dimension. Okay, and it is locally trivial for the usual topology on the base. So if I take any point in Y, then I can find a Euclidean neighborhood of this point on which the preimage is, it's isomorphic to a Cartesian product of this neighborhood times Pn. And if F is not equidimensional, then I can only find a birational representative of F, which has the structure I want, right? So it is birational to a projective bundle. In other words, I can find birational morphisms x prime to x and y prime to y, which are the horizontal arrows in this diagram, such that the vertical arrow on the left is a projective bundle, right? Moreover, I am able to find x prime and y prime, which are smooth. Right. So this result, in the case of a contraction of fiber type, totally classifies elementary Mori contractions of maximal length. They also proved something for birational elementary Mori contractions of maximal length. Namely, I am able to find something interesting if I normalize E. So E in that case is taken to be any irreducible component of the locus of F, so the locus which is contracted. I denote as Z the image of E, right? And if I normalize E and then I consider the fibration from, not fibration, but the morphism from E prime to Z, which can have, since I normalized E, which can have non-connected fibers, I can do the Stein factorization of E prime to Z, which factors through E prime to Z prime. So this E prime to Z prime has connected fibers, and this Z prime to Z is birational. such that E prime to Z prime is a projective bundle in this setting. Okay. Very well. So these two results by Höring and Novelli up to birational modification totally classify elementary Mori contractions of maximal length as, well, birational models of projective bundles. And as I said, when I say projective bundle, I mean something in which all the fibers are Pn, and which is locally trivial for the Euclidean topology on the base. It does not mean usually that the fibration is locally trivial for the Zariski topology. That's something a lot stronger, right? And usually being locally trivial for the Zariski topology, that's, well, a phenomenon which is obstructed by an element of the Brouwer group of the base, but I won't discuss that any further, right? But just keep in mind that if I only have the Zariski topology on the base, then my fibration does not need to be locally trivial for it to be called a projective bundle, okay? Okay, the two main ingredients that they used. Of course, so as I already mentioned, Ionescu and J that's the result that allowed us to well, them to identify the general fiber as a projective space.
Sorry, I have a question.
Yes.
Yeah, so in the previous slide,
Yeah.
so here, if yeah, you take a birational contraction.
Yes.
So, for instance, it can be divisorial, right?
Yes.
And so if E is divisor, so Z will be a point, for instance.
It could be, yes.
And if it is a point, so E will be a projective space? Or
Yeah.
what? Oh, okay.
Yeah. I mean, it would be normalized by a projective space in that case. It does not need to be normal.
Oh, yeah, I see.
Yeah, when Z is a point, this result exactly says that E is normalized by a projective space. So it could be, I don't know, like a nodal cubic, like a nodal cubic curve. I don't know, whatever you want.
I see. And if the contraction is flipped, so in this case, can we have like special structure or?
I don't know. I haven't thought about flips. They do not say anything about flips in their paper.
Okay.
Yeah.
Okay, thanks.
Of course. So the first main ingredient, as I said, so this result by Ionescu and J from 2002, allowing to identify the general fiber as a projective space. And now that I know that the general fiber of positive dimension, of course, in the locus of F. So now that I know that the general fiber is Pn, I want to identify the special fibers, so the singular fibers, I mean the fibers on which this result does not apply, okay? So this amounts to degenerating projective spaces. And if I degenerate the projective spaces with this length condition, so the following condition according to which I have an equidimensional fibration over something normal. Okay, in that lemma, x and y do not necessarily designate the same x and y as earlier. This could be x could be the e that I have. Okay, so maybe that's a bit of a mistake by me. I should not have written this x and y, but okay. If I have an equidimensional fibration with general fiber Pn, and I have a relatively ample line bundle on x, such that among rational curves contracted by F, so F is this fibration, right? So if I have a relatively ample line bundle such that among rational curves contracted by F, L has its smaller degree on the lines on the general Pn fiber, right? Then all the fibers are irreducible and normalized by Pn. Okay, and then with a little bit more of work, they managed to construct this birational model of my elementary Mori contraction, which was a projective bundle. Okay. So, and this lemma, the proof of this lemma is not very, that's not theoretical at all. That's just a computation and the use again of Ionescu and J. Okay. Okay, so this concludes their work on the study of, well, the case of maximal length, and that's a result which is, well, it totally classifies the elementary Mori contractions up to birational equivalence. Okay, so what remained to be done was to move on to the submaximal case, for instance, right? Which was my focus. So first, let me introduce a little bit of notions and the computation. So if I have an elementary Mori contraction with submaximal length, meaning that, as I said, the length is equal to its upper bound minus 1, and I assume F to be divisorial, right? So this hypothesis is going to turn out to be very useful. As it was already mentioned, divisorial means that F is birational and the locus contracted by F is a divisor in X, so a hypersurface, right? Then I denote as E the locus of F, which is irreducible in that case, thanks to a result which can be found in the book of Olivier Debar. And minus E is relatively ample. Okay, so this fact that minus the exceptional divisor is relatively ample is something very common that we can find when we blow up something on the smooth locus, for instance, right? And another thing that I need to introduce is the notion of deformation families of rational curve. So this is due to Grothendieck, but it is very well explained in the book by Collard on rational curves in algebraic variety. That's the book by him from 1992. If I have a rational curve, so rational curve, just imagine something normalized by P1, right? A rational curve in a variety, then this curve is represented by a point in a space which I denote as rad curves. So that's the space parametrizing rational curves in W, and this can be expressed as this quotient. On the top, Hombir, that's the space which parameterizes morphisms from P1 to W, which are birational onto their image, right? And I mod out by automorphisms of P1. Okay. Right. And this point in this space, if I consider any, an irreducible component of the closure of this space in the Chow variety of W, an irreducible component containing this point, then I call this component a deformation family of gamma in W. And since I have taken the closure of this space, then I can have points which are in the limit, right? And well, these points which are in the limit, they parameterize not necessarily rational curves, but degenerations of rational curves. So these would be one cycles, which are sums of curves which are also rational, right? But I can have more than one component when I generate a rational curve, okay? Okay. Well, what do I know thanks to this? If I have a rational curve in a variety which is Gorenstein, so Gorenstein means that the canonical is Cartier, right? It means that the canonical line bundle is well defined everywhere, right? And this curve meets the smooth locus of W, then I can find the deformation family of this curve in this variety such that this. So the dimension of H is larger than this. And the -3 here is a reminiscing fact that I quotiented by the automorphisms of P1, and this group is PGL2, which has dimension 3. Okay. So this is an inequality in one way, and I have an inequality in the other way, also by, so that's another result by Cho, Miyako, and Shepard-Baron. If I have a normal variety W and a rational curve inside W, such that gamma is minimal, it has minimal degree against an ample line bundle among rational curves, then any deformation family of gamma in W has dimension lower than 2 times the dimension of W minus 2, and the equality is met if and only if W is Pn and H is the family of lines in Pn. Okay. Otherwise, the equality is strict. Okay. And these two inequalities will turn out to be very, very useful, because now what we need to do to identify, well, the general fiber when it is a projective space, to identify this, we only need to compute dimensions of deformation families, right? And if we meet the upper bound, that we know that the general fiber is Pn. Okay, so now let's carry on with the computation. So I have my elementary Mori contraction, which is divisorial from x to y, and E is the extremal divisor, which is, as I said, irreducible, so I have only one component. I denote as Z the image of E in Y, and the equidimensional locus of E to Z as EEC to ZEC. So by equidimensional locus, I mean that I only keep those fibers with pure dimension equal to the expected dimension of E minus dimension of Z. If I have any fiber containing a component of large dimension, then I remove this entire fiber, right? Okay, and well, preliminary lemma. I know that I've proven that if I have this, well, if I have the now that I have defined this equidimensional locus, I know that the minimal curves, so that's rational curves contained in E, on which minus kx has the minimal degree. These curves cover entirely the equidimensional locus. And moreover, I know that any fiber, even the fibers of larger dimension, any fiber contains a minimal curve. Okay. And the computation is as follows. I consider F to be in E the general fiber of the equidimensional locus, right? And I take gamma to be a rational curve in F which is minimal and which meets the smooth locus of F. And this curve exists thanks to the above lemma, right? Then I can find the deformation family, well, of gamma in F satisfying this inequality. That's thanks to the result by Collar, which is here, right? Okay, but I know that minus kf I can obtain via adjunction if I've taken my fiber F to be general enough so that it is locally complete intersection in E. Okay, in that case, minus kf is equal to the restriction of minus kx minus E to F. And by the submaximal length hypothesis, I have minus kx times gamma is equal to the dimension of F minus 1. So, yes. And this gives out this following chain of inequalities. I have this first inequality, which is thanks to Cho, Miyoka, and Shepard-Baron. And this second inequality follows from the one on the top, right? And in the end, what can we conclude? We can conclude that minus E times gamma, which is relatively, minus E is relatively ample, so minus E times gamma is positive. This can only be equal to 1 or 2, right? And well, these are two cases to discriminate, right? And if minus E against gamma is equal to 2, for instance, then we are in the case where I find the deformation family of gamma in F, which is equal, whose dimension is equal to 2 times the dimension of F minus 2. So that's the case where F is a projective space, right? And when minus E times gamma is equal to 1, then this requires a little bit more of work. Okay. So let's carry on. In the second case, not the first case, in the case where minus E against gamma is equal to 2, then what I need to do is consider the normalization of the equidimensional locus and the normalization of its image. Then this fibration E prime over Z prime is a projective bundle, okay? So that's something inside which all the fibers are Pn, and it is locally trivial for the Euclidean topology as, well, these are algebraic sets, so complex algebraic sets, right? And in that case, so all the fibers are projective spaces, and generically as E prime and EX are the same, well, the general fiber of EX to ZX is a projective space, and gamma inside this fiber is a line, since that's a minimal rational curve, right? So a line. And in this PN fiber, in which gamma is a line, since minus E against gamma is equal to 2, then we know that minus E on this fiber is the polarization O of 2. So that's the polarization of quadrics, right? Okay. And for E prime to Z prime to be a Zariski locally trivial projective bundle, I need the existence of a polarization, which is the hyperplane polarization on the general fiber, but I do not have this. I only have something minus E, which is, the quadric polarization on the general fiber, right? Okay, so to be Zariski locally trivial is a much more stronger statement. But it holds if I have a tinier additional assumption, which is that the relative dimension is even. So if the relative dimension is even, I do not even need to normalize. I just consider the equidimensional locus of E to Z. And I know that this vibration is a projective bundle, and it is locally trivial for the Zariski topology, right? And in that case, it means that there is a line bundle on EX which has degree 1 on all the lines contracted. And this polarization I usually call the relative hyperplane polarization, right? And this makes EX isomorphic to the projectivization of a vector bundle over ZX. Okay. Well, and this assumption, when the relative dimension is odd, well, we can expect the same phenomenon to happen, but I haven't managed to prove it, so the question remains open, right? Okay, so in general, we need to normalize. Okay. What's of the other case? So that's the case where minus E against gamma is equal to 1. So in that case, I did not write it there, but in that case, when minus E against gamma is equal to 1, the general fiber of E to Z can either be isomorphic to a projective space or to a quadric, right? And in both cases, gamma, which is a minimal rational curve in this fiber, is a line, since quadrics are also covered by lines, right? Okay. Well, in that case, I prove that the general fiber is, in fact, isomorphic to a quadric. And it's not possible that the general fiber is Pn, okay? And since the general fiber is a quadric, then the question arose, is it possible to find a birational representative which is a quadric bundle? And the answer is yes. By quadric bundle, I mean something which is embedded in the projectivization of a vector bundle, right? Such that all fibers are embedded as quadrics. And this is true if I consider this birational modification of ZX, which is Z prime, right? And over Z prime, I consider the fiber product and I normalize it. Then the normalization of this fiber product is the normalization of an actual quadric bundle over Z prime. This is summed up in this diagram. So I have my equidimensional locus over ZX. I have taken this birational modification of ZX, and E prime is the normalization of the fiber product of these two guys. And this normalization is the normalization of a quadric bundle. But a priori, this does not tell that E prime can be embedded in the projectivized bundle. Well, usually Q is not normal, so Q and E prime are actually different. There are also cases where E prime and Q are in bijection, so this normalization morphism is a bijection, but not an isomorphism of algebraic varieties. Okay, that's a very fine situation, like very fine discrimination. Okay, and this birational modification z prime of vz, which I have, its existence is given by, well, that's a result by Ugo Rossi from the 1968. Okay, and I call this modification the locally free birational modification of the direct image f star of minus e. So on EX, consider the polarization minus e, which, as I said, is relatively ample and has degree 1 on the lines. Okay, so that's the candidate that you would want to have as the relative hyperplane polarization for the quadric bundle that you want. Okay, and this polarization then, well, usual procedure for constructing projectivized bundles, you take its direct image on ZX via F. This direct image does not need to be locally free. Usually it's not locally free because you can have special fibers on which minus E has more sections than on the general fiber, right? And well, if the direct image of minus E is not locally trivial on ZX, you can find a birational modification of ZX. So this morphism is an isomorphism on a dense open subset and a vector bundle over Z prime, which generically coincides with your direct image, right? And well, this vector bundle that you have, if you projectivize it, then you obtain this bundle in which the quadric bundle is constructed. Okay. Moreover, we have, well, a behavior which is very similar to the behavior of a regular quadric bundle. So this applies to EX over ZX. If I have a fiber which is reducible, so more than one component, then it has two irreducible components, right? And both components are normalized by Pn. Okay, so as I said, that's a behavior which is similar to the usual behavior of a quadric bundle, but it's, well, this statement is weaker since these two components do not need to meet along a hyperplane, right? They can even meet along just a point, okay? And they are not necessarily normal, but we know that they are two and they are normalized by Pn. Okay. As I have a little bit more of time, I can talk a little bit more about the case where f is not divisorial. Okay, so let me go back. So is everyone happy so far? Or are there any questions? Okay. Okay. So I want to go back to this computation. Okay. So as I said in my work, so this work which I just presented, I assume that f is an elementary Mori contraction which is of submaximal length, and I assume that f is divisorial. So it is birational, and the locus contracted by f is a hypersurface in X. Okay. Well, this hypersurface E turned out to be very useful since I have this discrimination of two cases, right? But this dichotomy, well, we can also have a dichotomy if I assume that f is not divisorial, but if it is birational and the locus of f is complete intersection in X. Okay, so it can have more than, the codimension can be more than one, but if it is cut out by hypersurfaces, so if it is a complete intersection, then I have well, a similar inequality. So the left part of the inequality doesn't change, okay? Since, well, this applies to any variety which is normal, I can consider a general fiber inside my irreducible component, which is normal, right? But on the right part, instead of E, since I have a locus which is, well, just a complete intersection with possibly codimension more than one, I would have, well, 2 times the dimension of f minus, so this would not be equal to 4, but this would be equal to 2 minus the codimension of E in X minus 1. And this would be just the sum of all the hypersurfaces cutting out the locus of f, right? And in the end, what I would obtain is I would obtain that I have such a dichotomy for some intersection being equal either to 1 or 2, and if it's equal to 2, then the general fiber is a projective space. And in that case, the second part of this statement would immediately be true. Namely, if I have something where the codimension of the locus of f is more than 1, if the codimension is 2, for instance, and the locus of f is cut out by 2 hypersurfaces, then I have at least one of them which plays the role of my relative hyperplane divisor. So E-ec over Z-ec would be immediately a projective bundle, which is locally trivial for the Zariski topology. So E-ec would be the it would be the projectivization of a vector bundle, right? So this I have managed to prove when the codimension is more than 1. In the particular case where the locus is a complete intersection. Otherwise, I think the case where the locus has codimension more than 2 and is not a complete intersection, this requires to develop new ideas, which I haven't had so far, but okay. Very well. I think this is all I wanted to say today, so thank you very much for your attention.